Hello, this is Emmett, and today I'm presenting Lab 2 on motion of a falling object. The object I chose to observe was a ping pong ball dropped from a height of 1.167 meters. Here's the tracker footage of the ping pong ball being dropped. In order to measure the data in terms of real-life perspective, I rotated the axes so the ball is falling in the negative y direction. Next, using skeleton code given to me on my online course, I create a model of the falling ball. I set the mass equal to the mass of the ping pong ball I found using a precise scale. I also use the initial position and velocity data found using the tracker information seen here. I also made equations to measure the net force by adding together the force of gravity, which is represented by W here, and the drag force, represented by Fd here. Using the net force, we find the velocity of the object at time t and loop it. Here is the model being run. Alright. As you will see here, the arrow pointing upward represents the drag force, and the downward arrow represents the force of gravity. You can see that the downward arrow is constant, while the arrow representing drag force increases as the magnitude of the velocity increases. Using data from the experiment, the computational model without the drag force taken into account, and the model with drag force taken into account, I made this graph. As you can see, the experimental data and the model taking drag force into account match up much better than the experiment's data and the model accounting only for gravitational force. My experiment's data overshoots both models' predictions, but not by much. This could be caused by human error when marking points on tracker, or by filming the falling ball on not a perfectly perpendicular plane. One of the reasons the data matches so well between the computational model and experimental data towards the end of the graph is because in order to find the coefficient of drag force, I used a guess and check method to match the distance fallen between the experiment and the model. The variable b, seen here, represents the coefficient of drag force, and that is fit into this equation. Fd equals negative b times the magnitude of the ball's velocity times the ball's velocity in vector form to find the drag force. The graph here shows position versus time, and in order to see a graph of velocity versus time, you can simply look at the slope. As you can see, the model position that does not take drag force into account seems to have a increasing or decreasing slope consistently through the graph. However, when drag force is taken into account in the orange line, you can see that the slope seems to even out towards the end, hinting that it may have reached terminal velocity. The question is posed, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Since the force associated with the object being thrown is instantaneous and doesn't remain after the ball has left the hand, it will not affect the terminal velocity. The act of the ball being thrown only affects the net force while the ball is still in hand. The only effect of throwing the ball downwards is the rate at which terminal velocity is reached. Terminal velocity is determined by velocity instead of acceleration. Thanks for listening along with me today, guys, and I hope this presentation was informative for y'all.